Okay, let's get started. Let me have your attention, please. Let's get started. Welcome to the University of Tennessee Nuclear Engineering Department Colloquium Program. My name is Lee Dodds, and it's my privilege to introduce today's speaker, who is Ms. Cindy Kelly. She is the president and founder of the Atomic Heritage Foundation in Washington, D.C. Cindy received a BA in History from Wellesley College in 1968, and then an MA in History from Yale University in 1969. She then worked for almost 20 years for the Environmental Protection Agency and followed by 6 years for the U.S. Department of Energy. She retired from DOE in the year 2000, and then for a couple of years she worked for the National Trust for Historic Preservation until 2002. And then in 2002 she founded the Atomic Heritage Foundation. Her topic today is Race for Atomic Power. Ladies and gentlemen, please welcome Ms. Cindy Kelly.
Thank you. Thank you very much, Dr. Dodds. Is this microphone working? Good. Okay, great. Well, welcome. I don't know what generation of nuclear engineers you'll be. I assume everybody in this room is destined to be a nuclear engineer. Is that right? No? Some? Some of you? Most of you, okay. But I am very pleased and privileged to have known some of the very first nuclear pioneers, as we call them. I mean, many of them were not nuclear engineers because they didn't have that discipline. They were chemists. They were engineers, civil engineers. They came mathematicians. They came from a variety of backgrounds. And what I'm going to do today is going to be a little jumpy, but I think you'll appreciate it because we have cobbled together little excerpts from my interviews with many of them. The Atomic Heritage Foundation, which I founded, was partly founded because when I was with the Department of Energy, I was basically appalled that they didn't have more respect for their history and that they were going to bulldoze the last remaining of the Manhattan Project buildings at Los Alamos. Under then Secretary Bill Richardson, we were able to get a group together in the department and agreed to look for money. And there was a new program called Save America's Treasures. And that provided $30 million for federal agencies who had historic properties that were in danger of being lost. And because we qualified, some of them were going to be bulldozed, and some of them, like the Experimental Breeder Reactor 1, the first built to prove the principles of commercial power, were in disrepair. We submitted applications for that and other things. So we had 7 applications in, and we got 2 awards, which is quite exciting. One of them was for this Experimental Breeder Reactor, or EBR-1. How many have heard about EBR-1 before? Oh, good, great, okay. You're familiar. At any rate, it was, first thing we did was do a video using 6 people who actually were on the team that went to Idaho and built the EBR-1 and worked there, as the first people to develop such a reactor. So you'll meet Kirby Whittam, Reed Cameron. You'll get to know them. They look a lot older now than they did in the 1950s, but they have just as much spirit and enthusiasm for what they did. You'll also meet, we were, once this money, my challenge was to get the matching grants. That's why I left the government, because we were in a catch-22. We had this grant awarded, but it was a challenge matching grant. We had to raise equal amounts of non-federal funds. And as a federal employee, I couldn't solicit funds, and I couldn't use federal funds to pay anybody else to solicit the match. So on to a new career. But fortunately, it all worked out, and we were able to match the funds. And then we began new careers as museum exhibit creators and documentary film producers. So we ended up putting together companion museum exhibits, one at the EBR-1 itself and one at the museum in downtown Idaho, on the whole history of this remarkable period. As I said in the little abstract, James Schlesinger, who was at one point chairman of the AEC, as well as secretaries of defense and energy, said that it was the history of the early development of nuclear reactor technology was as if you took aviation history and compressed it in 20 years. You went from Kitty Hawk to a Boeing 747. That was how fast we moved ahead in this whole technology. And I think I think you're on the crest of a whole new adventure. I mean, in terms of developing the next generation, if you like, or what the 22nd century or the remainder of the 21st century will use in terms of power. But you'll see the excitement that these people shared with respect to their pioneering jobs. At any rate, shall we can begin? The whole history of nuclear power is interlaced with war. Somebody said it's too bad you only have one chance to make a first impression, and atomic energy was introduced to the world in the form of a bomb. But that's the history. And right before World War II broke out, of course, fission was discovered. Then our country invested in the Manhattan Project, which was the top secret effort to make an atomic weapon. But while they were making it, the leaders such as Enrico Fermi, brilliant Italian physicist at the University of Chicago, and his right-hand man, Walter Zinn, were thinking on trying to figure out how can we use this power for civilian purposes, and we're drawing the blueprints for that first reactor. The AEC took over from the Manhattan Project in '46, and then decided that they need a safe place to test these. They were thinking of Oak Ridge, actually, but people thought that's too close to populated areas. We need a remote place, and this is what they picked. It's a desert with water, basically. There was a proving ground, a naval proving ground out there. Big guns were fired to try to test and recalibrate these guns. So the government owned it, and the local population embraced this idea of having a new mission. It was isolated, had good transportation, sparsely inhabited, and so forth. So they started. And the story that we looked at was how this merger of the federal government's effort and the sort of agricultural area of Idaho transformed that area and the people in it. And so this first little video will give you a sense for that.
The AEC needed a home for the many experiments and tests that lay ahead. In 1949, they found an ideal location for the nuclear reactor testing station 29 miles west of Idaho Falls, on a piece of land that once had accommodated the naval proving grounds. Here could be found the available power, abundant water, and isolation that the station would need. There were also nearby communities that could grow with the site.
Idaho Falls fought for it in a major way, and so they were thrilled when the AEC came and called Idaho Falls their headquarters town.
Not only did it bring jobs, it brought scientific opportunities, which you did not find very often.
They saw the opportunity for breaking into the growing technological framework of the country.
As the western outpost of Chicago University's Argonne National Laboratory, the testing station began filling out its team. But while Idaho provided the perfect backdrop for nuclear experimentation, it was a desert. And in the eyes of many Easterners entertaining the thought of joining the testing station team, Idaho looked barren and unappealing.
I was hesitant at first because my wife was from South Carolina and she was used to anything but the desert. But I took her some pictures of the nice cultivated grounds around here and convinced her to come.
First impression we got, of course, we got up here in the dead of winter, of course, in January, and took a look at that snow pile high up on the windows and everything. And, again, my wife was ready to go home.
In the end, it wasn't the snow or the desert, but the nation's call to be part of scientific history. It was just too tempting to resist.
Most scientists, if they're worth their salt, can't leave the experiment alone. And so what happened here's 52 reactors being built on the NRTS, and here are scientists who are not going to sit by the telephone. Here they come.
It was a great time to be involved with new science. The nuclear industry was just in its stages, really. The terrific number of engineers and physicists and chemists that made their home here, the high level of achievement that took place here, and the excellence with which science was conducted. This was world class.
Level of personnel from a standpoint of technological and scientific background made a good impact on the educational system in the city and eventually in the state.
I can't imagine how many hundreds of people took advantage of the education program from the site, and it probably increased the education level of this area by 200 or 300%.
Given the means and freedom to pursue their goals, the testing station's impressive blend of local and relocated intellect set about its mission. They tested theories, challenged conventional thought, and aggressively tore down obstacles.
So it was quite an exciting time for both parties. The people who were in Idaho, and you'll see from other videos how they got their talents were utilized and integrated into this work. But now we're going to talk about Zinn's infernal pile. Everybody knows the word pile, right? What was the first pile? Yes, Chicago Pile 1, CP1. At any rate, they hadn't come up with a reactor, I don't know, but anyway, they called pile, and Zinn's infernal pile, again, this is Walter Zinn, a Canadian, who was appointed director of the Argonne National Laboratory. This is how science was transformed in the United States. We were in the backwater before the war. There was very little federal funding. But with the Manhattan Project, which was huge, $2.2 billion, which is about $20 billion in today's terms, and its success and the sort of prestige it brought to the United States to be the only industrial country that succeeded in that effort during the war, the federal government recognized that science and technology is key. And so they invested in the national laboratory system. And Argonne and Brookhaven in Long Island were two of the first national laboratories created, as they realized that this high energy physics, this new physics, not every university could afford all of the reactors and accelerators and whatever needed to experiment. So they created that. At any rate, Walter Zinn was the first head of that Argonne National Laboratory outside Chicago, and he was hands-on man. He spent a lot of his time in Idaho building this first reactor. And it had many firsts, as you can see. It was the first to produce usable quantities of electricity, and 4 little light bulbs. The light bulbs are still there. It was the first one to breed fuel, and I know you all know what that means, right? And the reason they chose a breeder was that they thought that uranium was in short supply. They really hadn't figured out that we, the United States and the West, had a lot of uranium and uranium mines during World War II, we depended on Belgian Congo, Canada. We discovered Grand Junction in Colorado as a source, but there wasn't as abundant, or we didn't realize the abundance of uranium. So the Army, once the Soviets were in the game for real with their detonation of Joe 1, their first atomic bomb in August of '49, the race was on. And the Army laid claim to the uranium. So those scientists who wanted to pursue the civilian route, they were said, it's not going to be enough uranium to do both. Build up the arsenal we need of the weapons and to supply whole new civilian power. So the key was this breeder reactor that could, use the plutonium to irradiate the uranium around a blanket, the U-238, the inert uranium, and create fissile uranium and kind of have a perpetual motion machine. Anyway, it worked. It was really quite exciting. And here are a couple of the people who worked on it telling you about how it was designed.
The core is only about 7 inches by 7 inches. 7 inches high, 7 inches diameter. It's down below that floor level. Nobody was really knowledgeable in the shielding of a fast reactor. The fuel elements have a long stainless steel shaft about 8 feet, and they're just shielding to keep the gamma rays and neutrons from coming up in that core region. This is W shielding, the foot layer on top. It's steel plate and masonite. And the masonite slows neutrons down and the iron absorbs them. We never had to put any shielding on it. HP's lived with it. This was heavy concrete with a lot of ball bearings in it, and it's a good shielding. So this thing does get a little radioactive, but not bad.
Let me just give you an example of a safety feature that was incorporated into EBR-1 that was very basic. When you shut down a nuclear reactor, it does not stop generating heat because there is radioactive decay going on in the material, and that generates heat. EBR-1 was designed in such a way that come hell or high water, the cooling would continue. In fact, that reactor was only run on an 8-hour-a-day basis, and the plant naturally took care of the cooling by natural convection. We had one valve we had to open before we left the plant, and that converted the system to a natural cooling system, not requiring any pumping of the NAC at all. Just natural convection would dissipate a little bit of heat to the building. And that was a standard practice. Every night we went home, we pushed the button to turn on the cooling system. You could hear it all over the building. We said, it's time to go home. Zinn insisted that building be completely locked and the gas locked out of the building because he didn't want anybody in there fooling around with the equipment. So that's how conservative we were with respect to designing that plant, so you could literally shut it down and walk away.
Let's see, next slide. This is wonderful being an audience that knows what NAC is without having to explain it, right? Does everybody know NAC? Terrific. Anyway, but it was tricky stuff to work with. It's the first time they worked with it. They had to figure out how they could avoid having mechanical pumps that might get, might break down. They were very ingenious. And you probably know about the blanket that was around it. And then they didn't have, there wasn't stuff you could buy off the shelf, except if they thought, well, gee, if I went to get my car repaired, they have hydraulic pumps to lift your car up and down. So that's what they decided. They went to an automobile repair shop to get the pump that they used for this shield. Anyway, I'll let them tell you about that.
There's a reason that EBR-1 was the first reactor to produce electricity, and that is that it's among the simplest to design and to operate. EBR-1 and EBR-2 are cooled with liquid metal. Liquid metal brings no pressure boundary that has to be dealt with in design.
The NAC is liquid. It looks like mercury. It's nice and silvery, and it flows at room temperature. But if you have it in the presence of air, it'll smolder, and if you put it in water, it becomes an explosive mixture, and it'll just blow up. Everything in here was brand new as far as concept goes. I don't know, other than that each component would have been used in industry someplace for some situation. But concept of taking a piping system and taking heat from a heat source that was not coal, or not gas, not a fireplace or a furnace, and transferring that heat to a turbine was all brand new. We had to figure out how to use the NAC in pipes. We had to make sure that these pipes of this size and diameter were sealed with the metal flanges. It could leak out of there. We had to make sure these seals worked. The NAC could crud up those seals, and when the NAC oxidizes, it's like lava, and it just chews that seal up. That was the problem I had in the equipment for putting the NAC in the fuel to build the fuel elements.
So they were your age, just about, when they were trying to solve all these problems. They had fun. In fact, they told me that sometimes they'd put a little knack out and they'd throw on a fence post and they'd throw snowballs at it and watch it explode. Some of the bad boys did that. They had some fun. At any rate, do you want to? Well, we could watch the next one. The next slide. It's that one of the messages is. Well, I don't think we make it perfectly clear, but the experiment that resulted in the meltdown was a deliberate one. They knew they were risking this meltdown. They thought that they could stop the reactor just in time, but there was a miscommunication. But it's been later, kind of presented as, wow, a big mistake. Well, it wasn't. It was deliberate. And there was this miscommunication, but it's an interesting story.
The vision was to proceed with the development of nuclear power in a way that could provide essentially limitless energy. It would do this by actually producing more fuel than it consumed. It was this concept that was explored initially by EBR-1.
There were many firsts associated with EBR-1. One was the first reactor in the world to produce useful electricity from nuclear power, and it was a fast breeder reactor.
At one point, there was a miscommunication between the scientist running the test and the actual operator that was doing the controls, and EBR-1's core melted. From that, we learned how to change the way the core was built so that you couldn't get into that unstable area anymore.
We started up the experiment. They were going to run it for 500 seconds, and they watched the reactivity as the reactor heated up, as the power went up. It was going up faster and faster on the curve. So Lichtenberger was there, and he said, take it down. Well, take it down was not in our nomenclature. The operator didn't know what he wanted. I mean, if he wanted a scram, everybody knew what a scram was. There was a handle in the control room ceiling where any one of the 7 physicists could have reached up and scrammed it. Nobody had the presence of mind to scram it, including Lichtenberger. So the power went to the point of inflection, started down, then it turned around and started back up. And it started up in earnest. I mean, it was going. Then the thing scrambled itself in about 500 seconds from the time the reactor went up to critical. And that was it.
At any rate, let's see, go back to the slides. Well, EBR-2 is a reactor that probably this room knows about. Do you know about EBR-2? Yeah. It's quite a story. I mean, it was Leonardo da Vinci was looking for the perpetual motion machine, and this was it. It ran from 1964 to 69 on the same fuel. It's a 31-day process of taking the fuel out, all remote handled, and then it was chopped up, and the spent fuel part was separated, and the fuel rod was refabricated and reinserted in the reactor, and it ran seamlessly for 5 years. It's interesting because that's kind of what people are talking about now. I mean, what President Bush is saying, this is what we need. And it was something that was very successfully done and proven as part of this series of 52 experimental reactors in Idaho. In 1986, there were tests that demonstrated that it was inherently safe, that it shut itself down. And there's people in the audience, while they tested this and proved it. But it was only 3 weeks before Chernobyl. So all of a sudden that captured the public's mind, and they were nervous about things nuclear. So that kind of got overshadowed. But it really was a major milestone, and it's something that presumably you guys will reinvent in the near future. Next slide. The materials testing reactor was the second reactor built at the site after, well, actually at the same time as EBR-1. EBR-1 was built in 51 and operated until 64. The materials testing reactor came within months. But they didn't know anything about the materials. What one's going to hold up? What ones are going to shield the naval crew? The Navy was a big customer of the work done at this reactor to figure out what the shielding material should be made of for the crews on the Nautilus and other submarines. All of the Westinghouse, General Electric, and all of the companies, the power utilities that were getting in this game, and unlike France that kind of had a governmental sort of control over, all right, these are the models we're going to build and that's it. We love to encourage inventiveness, American entrepreneurial spirit, and it looked like a good idea. But the AEC was overwhelmed with all the different proposals for licensing, and they needed a place that these things could be tested. I mean, that really was the function of this National Reactor Testing Station that is now the Idaho National Laboratory. But anyway, this materials testing reactor really was a workhorse and a very, very important facility. Many others, we'll go to the next slide, we're trying to test the leading kinds of reactors being developed, the boiling water reactor and the pressurized water reactors. Anyway, borax was the name of the series. There were about 5 of them that were tested for the boiling water. And I'll let you listen to some of the people who worked on these. Reporters called these the runaway geyser because it spurred up in the desert when the reactors took off. Yeah, let's see, that's video 5.
Borax reactor experiments were designed to provide that experiential data.
They built a Borax 1 to find out what happens when they just drive that harder than they should and cause a steam explosion and blow it up.
And blow it did, sending up a geyser-like plume for the desert floor.
Reactivity accident could be something analogous to driving a car and the accelerator pedal goes to the floor at the same time that the foot can't find the brake. And so there has to be a very sharp increase in the power of the reactor. And the increase in power causes the fuel in it to heat up very rapidly.
Borax demonstrated that power excursions and coolant tests could be safely conducted in controlled environments. But it was Borax 3 that made the headlines. With help from Utah Power and Light, Argonne scientists used their boiling water reactor to provide electric power to the city of Arco, Idaho on July 17, 1955.
Okay, let's see, the turn to Borax 3. This is really kind of goes back to the theme that this was a competition with Russia for not only building up a nuclear arsenal, but kind of besting them in terms of being ahead on science and technology. And there was let me go to the next slide. There was a conference in Geneva on August 9, 1955, where we wanted to announce that we had lit a city. We use nuclear power to light up a city. And so they decided Arco, which was 600, but we didn't tell everybody it's really that small, was chosen because it was right next to the laboratory and its Borax 3 reactor. And the story is a little humorous in that because they didn't have FedEx, they didn't have overnight shipments, they had to ship out the film to show the Soviets and the other delegates, how we lit up this town early, a couple weeks early, and they hadn't actually done the experiment. So then it was a panic to actually do it. So we didn't say we did it not having done it, but the first time they tried it, it didn't work. You want to tell Gary? Do you want to show the video? It's kind of the story of the unsung heroes who were involved in this.
A normal Western community in a range and farm area with a normal quota of schools, churches, stores, and humans. Here was the chance to make one more small slice of history. Arco, Idaho could be the first American town to be lighted experimentally and exclusively by nuclear power.
The story of lighting Arco was interesting because the president was going to make an announcement in Geneva.
Since it was taking mailing time to get this film to Geneva, Switzerland, they decided to film a mock-up. An operator walk up and close a switch. And over in Arco, they use all blink the lights.
But under the direction of Argon, the system failed.
The reactor producing electricity was first connected to the grid that would supply power to Arco. It was connected out of phase.
The voltage waves of the two units have to be precisely together. And if they're not, there are horrendous magnetic fields and terrible physical forces.
There was such a reaction to the power line that it actually broke the cross arms off, which we spent all night and all day putting back together.
They wanted to have witnesses, you know, who would be able to attest at Geneva that this had been done.
Now we had to make it happen.
Another piece of plywood, put it on the stand, put a sinker scope and a switch handle on it.
And I told him, Charlie, you close the switch.
So the first lighting of Arco was done without the movie cameras and Digniture.
Arco sees new light on July 17, 1955.
It worked. The second time.
That described to me, certainly, this special partnership that exists between the practical capability in Idaho among so many people and the great talent in physics and science and technology that came from outside of Idaho.
Clancy Burns, the Utah Power and Light Man, had big headlines, picture in the paper and so forth, on him closing the switch that lighted Arco.
There were no thanks or good boys given out.
Well, he wasn't too happy about it, to be frankly, and I'm sure Argonne was not too happy about it.
That turned out to be a very complex thing.
2 years ago, they asked me to be the Grand Marshal in the Atomic Days Parade, which I did do. And I felt a little better about the whole situation.
Great. So as you can see, it's really fun to interview these people. The next program is SPURT, the Special Power Excursion Reactor Test. And you'll hear in a second Kurt Hare talking. And he, it's not in this, but he did say that in their work, they were allowed to do anything they wanted to do as long as we intended to do it. So that they had a plan and any experiment went. They had a great time with us.
SPERT was an acronym for the Special Power Excursion Reactor Tests. The purpose was to do increasingly severe accident simulations and see how the reactor responded. Started out with SPURT 1, which was a simple open pool reactor.
It was just a little hole in the ground backed by, I think, steel, and I don't think it was stainless, just steel. And it had water in it, and then a core in it, and it had a tin shed over it. That was SPURT 1. It was not very impressive.
Some people associated accidents in reactors with atomic bombs, and that is not possible. In fact, in the SPURT program, it took quite a while to figure out how to get to the point where one could conduct a destructive test. And one of these we did make the reactor blow up, as you will see.
From the control center, observers first saw the column of water rose to a height of about 80 feet. Clearly shown is the forceful impact of the water column on the upper bridge structure.
Kind of looked like Old Faithful. Really, if I can think of a simile, that's the best one I can think of. It actually bent the beams in the building.
They were showing that even if you do get this sharp increase in power that might occur when a control rod is ejected, that the fuel heats up, and as it heats up, it expands, and that's the same thing as turning off the gas and putting a brake on, and it just automatically shuts down.
Sort of the crown jewel of these experiments is LOFT, the loss of fluid test. It took a long time to design. They went through a change in the AEC leadership and the leadership at the laboratory. The wild and woolly days of the 50s and early 60s were kind of over. And everything had to be more carefully scrutinized and approved by various committees. But it was worth it in the end. I mean, they did some really terrific experiments in there through this program that were incorporated in the codes that are now used around the world. I mean, all of the experiments at Idaho, the borax, the SPERT, and the LOFT, and others became the foundation for these computer codes that operators use today.
Another important safety initiative was LOFT, the loss of fluid test.
LOFT, this was the crown jewel of nuclear safety experiments in the world.
The LOFT test was done very successfully with a consortium of international partners, and it established the data by which the modeling could be developed to aid in the design and protection of all of the reactors around the world.
They needed to actually know what would happen with a pipe break, and so the LOFT project was conceived and built and successfully tested.
It was especially important when one of these accidents actually did happen with 3 Mile Island.
Really, we learned a great deal, far more from our accidents than we do from just day-to-day operation. 3 Mile Island was a nightmare for public relations. It was a gold mine for technical folk.
And the information that had been developed in the LOFT test contributed greatly to the understanding of what had happened at 3 Mile Island, how to recover, and how to protect the fleet of reactors going forward.
I believe that we can look the citizens of the world in the eye and say that you and your children are safe from the consequences of any nuclear power accident, so long as you follow the pathway that we laid out, the codes.
At any rate, the civilian use wasn't the only use that was being pursued at the NRTS, but the military were, seized upon this. Admiral Rickover, whom I'm sure you've heard of, was really the father of the nuclear navy, and as early as 1950 had persuaded Congress that this program ought to be developed. And they broke ground for the S-1W, the submarine, first generation Westinghouse design. He actually had the Nautilus, the ship itself, the actual ship was built in Connecticut, Groton, but in Idaho they built a replica, an exact replica. So, and then they built the reactor to fit inside, the hull, I guess 2 hull sections they had there to test it. And they ran it, around across the Atlantic and back, a test run, a simulation. But he was incredibly exacting. One day he came to visit Idaho and he saw somebody's coffee cup sitting in this experimental area, and he said, "What is that doing?" And out it went. He was very demanding, and I think that his record shows it was a very, very successful approach. At any rate, the other services, Gary, can we have the next slide, were equally interested. Air Force, being one, they had a dream you could have a bomber that could circle the world 2 or 3 times. You wouldn't have to land. But it was way ahead of the science, the material science. The scientists in the Manhattan Project that I've been dealing a lot with over the years, because that's the other sort of thrust of our organization, they were outraged that the government were pursuing this bomber. They thought it was ill-conceived. Hans Bethe, who just died recently and was one of the giants of the Manhattan Project at Los Alamos, he actually wrote me a letter and said that he and ace flying Air Forceman Jimmy Doolittle went to President Eisenhower in the early 50s and asked him to stop this program. It did not make sense. But it had the support of the leaders of the Air Force, and they didn't want to be bested by the Navy, and so it went on. It wasn't until President Kennedy was in office. I think he canceled it in '61. But anyway, it was not there are some phenomenal artifacts, like this huge hangar built in Idaho still stands. It's all shielded. You can see it from satellites, and it's quite a structure. But and they learned a lot about high temperature materials and metals. So they learned a lot, but it was didn't fly. Bomber that did not fly. The Army was also very interested in their. Gary, do you want to do the next one? They were looking at a small portable reactor they could use, in the Distant Early Warning System in Alaska. SL-1 was a prototype. You may have heard about that. How many have heard of SL-1? Yeah, all the tragedies get a lot of coverage. I have a little video on that talking about how 3 servicemen were killed in this accident that still remains a mystery today.
The interest of the Air Force was in atomic power to propel an aircraft that would be able to fly very fast and remain aloft for days at a time. The Army also, I might add, had interest in nuclear power. They wanted to do any number of things with small nuclear power plants. Could you have a nuclear power plant that was so small that you could actually make it portable? The interest of the Navy was in submarine propulsion. The real birth of the nuclear Navy, the demonstration that nuclear power could propel a submarine, was really proven here.
Stationary low power reactor number 1, called the SL-1, had blown up and killed 3 servicemen who were operating it at the time. The Atomic Energy Commission came to us at General Electric and said, "You have the biggest hot shop in the land. We'd like you to clean up this SL-1, take the whole reactor in that hot shop, and tear it apart and find out just what happened."
They believe an operator pulled the control rod out rapidly. At that time, that particular core could go critical on one rod.
One of these servicemen was supposed to lift up a control rod 3/4 of an inch or so. Instead, he lifted it up 20 inches. It weighed 75 pounds, so it wasn't an easy job. To this day, we don't know why he did that.
Produced a steam explosion, heated up the water that was in the reactor, the water turned to steam.
And it made a water hammer, and it pushed that water up with such force that when it hit the top of the reactor vessel, it raised it completely up out of the ground, clear to the ceiling of the building, because there were control rods sticking in the roof of the building.
The person who was standing near the control rod was instantly killed, and the other 2 also died.
Of course, everybody says he was trying to commit suicide and kill the other 2. We did some tests with him with a control rod, and it appeared to us that it was sort of casually lifted. It wasn't lifted as far and as fast as you could move it if you were really determined to do that. But to this day, we still don't know the reason for it.
Really, we learned a great deal, far more from our accident than we do from just day-to-day operations. We began to see things that could be done to make a reactor less susceptible to those kinds of accidents. The EBR-1 reactor, when it melted, we learned how to fix it so it wouldn't do that. So you couldn't get into that area of instability that it had. Now, with the newer designs, the inherent safety characteristics that are built in, you can rely on things like gravity, which is generally going to work.
The SL-1 reactor building has been dismantled and removed. But a scientific legacy remains for all who are charged with its safe operation
of nuclear reactors.
So that's your job. Anyway, I have a couple more. Just so I keep going, or okay. One of the things that was really remarkable about what happened in Idaho was that it created it was a crucible, international crucible for nuclear reactor development, and Walter Warren Nyer, who was in the white shirt, he was kind of a Johnny Appleseed. When they first started up, they get lots of letters saying, "Oh, please tell us what's your test result on the boiling water reactor experiments. Oh, could you write up? I understand you did a test on X, Y, or Z." And he responded, "Look, we've got to conduct these experiments. We don't have time to write up all these reports." But he would say to industry or governments, if you want to send us somebody who can work with us for the next year and a half, then we welcome them, and they can take home anything that they like. So people came from all over the world. It was sort of a United Nations of people working on reactor design.
Requests for NRTS results flooded in from other countries. But as Kurt Hare recalls, Warren Nyer had a ready response for those requests.
We don't have time to write up results reports for all of the specific needs. If you really want to find out what we're doing and get the benefit of our results, send one of your people here for a year. And needless to say, those countries, they pick the smart ones. So we had the cream of the crop coming in to work for us for a year or more, and then we're able to take it away and take back to their countries the results of this experimental program that we were running.
Virtually every developed country in the world had experiments at EBR-2. They had people on site at EBR-2.
And because of the visitors who were here, we did contribute to a lot of the knowledge to construction of reactors around the world.
And despite the fact I spent many, many years in the field of environment, I could skip over this. At any rate, they produced a lot of waste that was stored originally in shallow pits, but Idaho learned from Hanford, where the plutonium production site is in eastern Washington state, about not having liquid waste in underground storage tanks. So they developed a technique called calcining, and they turned it into a detergent-like thing, just like Tide. It's white, powdery substance that is not going to be, as long as it's in watertight containers, won't threaten the groundwater, which was a major innovation, and it reduced the waste volume by a factor of 7 to 1. And today, they're busy cleaning up. Over half the budget, I haven't looked at the 2006 budget, the 2005 budget was half devoted to demolition and cleanup. So they're now expanding the state of the art of environmental management issues. But just last year or the year before, Idaho National Laboratory got a new mission. They had been sort of consigned to be working on cleanup, and now they were told, you're going to be the place where this work is going to be done in the future for the future developments of nuclear reactors. And of course, just the other night in the State of the Union address, the president reinforced that commitment. Just one more slide summing that up. So we'll see, and it all depends on you to help carry forth and make this all happen. So at any rate, I know we've gone over. If you really like these shows, we have it all on a DVD. And also I have for you a special prize for coming today, which is a booklet in full color that sort of gives you photographs that's derived from the film and the museum exhibits, and has quotations from these people you just heard. So thank you very much.
Okay, we have time for questions and comments. I'll ask the first question, you think of the second question. Tell us a little bit about the foundation. Is it prospering? Are you being able to develop your museum exhibits, and how many staff members do you have? Or
Well, you know, small is beautiful. We're small. Right now, there are 5 of us, and we rely on student power a lot. We have some wonderful interns. In fact, the person who put this PowerPoint presentation together is an Arabic studies graduate student. So you never know where your future may be. But no, we have just gotten in 4 major new grants, which we're very pleased with. We'll be developing museum exhibits for the B reactor, you know, which was the first plutonium production reactor done at Hanford. And we're working with the National Park Service. We were able to get Congress to authorize and then appropriate funds to have the National Park Service study where there ought to be a national park site at each of the Manhattan Project sites. So that has just gotten underway, which is a big deal. I mean, from where we were, where everything was going to be torn down and everything, walk away and it'd be kind of like a park. We're getting, you know, more interest and visibility. The History Channel is about to produce a film on the Manhattan Project, part of a series called Lost Worlds. So it's perfect. It's focusing on, you know, plants or buildings or whatever that are about to disappear. And this is the case unless we get in there and preserve this history. I'm also, part of the work I did for the Race for Atomic Power, really can see the need for education, and I'm hoping that through the history of atomic power we can, you know, build on that and get more people comfortable with what it was. If everybody knew to what extent we had tested these reactors, that they would, I'm sure, feel much more comfortable about having one in their backyard. But I think, you know, you are a very fortuitous time in entering the field of nuclear engineering.
okay, Dr. Upadhyaya, just a minute. Wait a minute. Let me see. Yeah.
Your last slide showed something about the GNEP, the Global Nuclear Program. Who is running that program? The Department of Energy?
Yes, again, I meant to call someone and double check all of this, but that is from, the Department of Energy has an office of nuclear engineering that's in headquarters, Washington, D.C., and that is the group that's running the laboratory out in Idaho, which is, you know, where the major experimental work is done.
Okay, are there any other questions or comments? Okay, well, let me remind everyone that we do have a reception downstairs, and Cindy will be down there to join us, and you can continue talking with her one-on-one. But before we adjourn, let's express our appreciation to her for her presentation. Okay, thank you very much.